go to your calculator and type in 10 to the 100 plus 1 minus 10 to the 100. The 10 to the 100 said cancel, leaving 1, right? But if your calculator tells you 0, then you're probably the proud owner of an iPhone. And this is because Hans Boehm, a software engineer at Google responsible for how the Android calculator calculates, well, he has spent over 30 years of his career designing the ideal calculator app. It's a fascinating story, but I want to begin by telling you about how most software on computers is going to compute out basic arithmetic, something called floating point arithmetic. Take a number like 3.1415, the first few digits of pi. I could rewrite this as 31,415 times 10 to the power of -4. This is a floating point number, and it consists of these digits out the front that are sort of the significant digits. We call them the significant. The base, which in our case here is 10, and then the exponent, that's the -4. But if you're a computer scientist, actually most commonly you're not going to use base 10, you're going to use base 2. And so the standard implementation of floating numbers involves a significand, which can be 53 different binary bits, a base of 2, and then an exponent, which is 11 bits long. And then typically there's a plus or minus out the front, so 1 bit for that. That all adds up to 65 bits of information, but there's an extra rule in the significand, which is that the first bit is always going to be a 1, so you could sort of ignore that, leaving 64 bits of information, which the computer scientists love when things are sized in powers of 2. And what's incredible about these only 64 bits is that you can record an enormous range of numbers. You can have astronomically large numbers, as large as to the order of 10 to the 308. Microscopically small numbers, 10 to the -308. This whole range can be stored in just a very small amount of memory. But you can also do arithmetic on floating point numbers very fast and very quickly. Let's take our 3.1415, which we've written down in my sort of silly standard of floating point arithmetic with base 10 and 5 digits. And then let's add to that 0.01. So first step is write 0.01 as a floating point number in this format. So we write it as 10,000 times 10 to the -6. Now if I want to add them, I would like to just add the significance, but the problem is that right now the exponents are a little bit off. And so the rule is that you can adjust the smaller of the two exponents to become the bigger one. I'm going to rewrite 10,000 as 00100, but now it's 10 to the -4. The exponents are aligned. When you're doing your arithmetic, you're allowed to violate the rule that the first entry in the significand has to be something non-zero. Now I just add them vertically. I get 31515 times 10 to the -4, and my calculator app can display it on the screen as 3.1515. Okay, but then what was going on with that 10 to the 100 plus 1 nonsense? Okay, 10 to the 100 can be written in our way as 10,000 times 10 to the 96. I had to knock off a few because I went up to 10,000. The plus 1 can be written again as 10,000, but now times 10 to the -4. And what I would like to do is take those exponents and align them. But here's the problem. If I do that, the 1 is going to disappear. It just becomes 0,0000 times 10 to the 96. There's not enough digits in the significand, given the power of the exponent, to put the 1 anywhere. And so it just appears as a floating point number with these restrictions to be just the same thing as 0. You add those two things up, you get 10,000 times 10 to the 96, and this displays as 10 to the 100, giving us our formula that 10 to the 100 plus 1 minus 10 to the 100 isn't literally equal to 0, but via floating point arithmetic with those restrictions is equal to 0. And that's for the most part what the iOS calculator does. It does pure floating point arithmetic. But I want to show you some other options. First up, let's talk about rational numbers, numbers like a over b. Rational numbers are really great because I can just treat them as two unbounded integers that are as large as they need to be. I don't have to do any approximation when it comes to rational numbers. I can do things exactly. For example, let's suppose I want to add two rational numbers. Well, I find the lowest common denominator, the b times the d. And there's some additional computational layers, like I might write to reduce this, get rid of any common factors in the numerator and the denominator. I might want to spend some time calculating that. But the point is, all of these numbers are just integers. I can take up as much space in my computer, store them as I'd like to do, and I can get this exact answer as a rational number. Rational numbers are great, but for a calculator app, lots of things like pi and e and root 2s are not rational numbers. So if my calculator app was really good at doing rational arithmetic, that's great, but very limited. And there's actually a special category of rational arithmetic that's worth pointing out here. This is called the dyadic rationals. A dyadic rational is one where the numerator is an integer, but the denominator isn't just any integer, it's a power of 2. So all of these are dyadic rationals. A half, a quarter, 3/8, 7/16, anything like that where the denominator is a power of 2. You can probably guess that the computer scientists who like powers of 2 are going to like dyadic rationals. Okay, so let's take something that's not a dyadic rational, like how about 1/3? 1/3 is not a dyadic rational. Its denominator is not a power of 2. If I try to write 1/3 as a decimal, I mean, you know the expansion, 0.33333, it has this infinite decimal expansion, kind of annoying. If I try to write 1/3 in binary, sorry, it's also annoying, 01, 01, 01, 01, 01 on forever. Note that in binary, after we call it a binary point when it's in binary, they're all both powers of 2, right? 2 to the -1, 2 to the -2, 2 to the -3, and so on. Okay, so now I've given you all the tools to turn to Hans Boehm's paper, which I'll link down in the description, describes basically how the Android calculator works. The idea loosely is this. Let's take that 1/3 and let's try approximating it within 1, within 2 to the 0 to be a bit more precise. 1/3 is closest to 0. It's closer to 0 than it is to 1. If I was more precise, like I want to approximate to the nearest half or to the nearest 1/2 to the 1, it's closer to a half than it is to 0. And as you get more and more precise, the closest quarter, it would round to a quarter. To the closest eighth, it would round to 3/8. So the idea is that if you tell me an amount of precision, you tell me the denominator of the dyadic rational, I can tell you which specific dyadic rational with that denominator it's going to be. And so really what you have is a whole table of values. If you tell me the degree to which you would approximate, like 1/2 to the n, or in other words, how many points to the right of the binary point you want to be, well, I have this list of dyadic rationals that it's approximating it, and I can rewrite those in binary if I wish. So it's kind of like a function. You tell me an uncertainty, I'll tell you the corresponding dyadic rational. Okay, so more precise, these are referred to as recursive reals, and here's how they're defined. If I have some number line, first I'm going to do is I'm going to put some real number x on it. A real number that doesn't have to be rational, it could be something like pi. Then we're going to specify an uncertainty level. So a standard uncertainty would be of the form 1/2 to the n. It could be more general if you wished, but this is the uncertainty that we will use. So basically you start with your pi, and then you look a little bit to the left and to the right of that. That gives you your uncertainty band. And what we're trying to do is find the dyadic rational in there. So that's what we're going to do. We're going to choose the dyadic rational, so something of the form a/2 to the n, that's going to be inside my errors. And an example of that is something like 25/2 cubed. 25/8 is 3.125, pretty close to pi. And our restriction here is that the distance between the dyadic rational and x, so I use my absolute value here, the distance between the dyadic rational and x is less than my uncertainty of 1/2 to the n. Now, if you choose any error, there's actually infinitely many dyadic rationals in there. But the key to this formula is it's the same n that I'm using. If you've told me you want it approximated to with 1/8, the dyadic rational has to have an 8 on the denominator of it. And now this allows us to uniquely choose a specific dyadic rational from among the infinitely many that would exist if you didn't have that restriction that it had to have the same denominator. Now, I already suggested this kind of feels like a function, so I actually like this notation that's used in the paper, where it replaces an x with an f sub x, as in your real number is being represented by this function fx. And this function inputs an n, which corresponds to the error 1/2 to the n, and it outputs the numerator of that dyadic rational. Okay, so let's see our example concretely. So we'll go back to our example of 1/3 here. Let's assume we're rounding to the nearest quarter. As we've already seen, 1/4 is the value that is closest to this. And basically the restriction is that the difference from 1/3 of our dyadic rational, I'm calling it now f sub 1/3. This is the function representation of 1/3. When n is equal to 2, so all of our denominators are 2 squared, well, as we see, that's just the value of 1. So this is going to tell you how to compute that specific dyadic rational. But can we do arithmetic? Well, if I take something like 1/3 plus 1/3, look, you and I know that this adds up to 2/3, right? The algorithm might not know that, but you and I know that. And if we have 2/3, and let's approximate, let's say, to the nearest quarter, 2/3 approximated to the nearest quarter is 3/4, right? 2/3, its closest point approximated to the closest quarter is 3/4. So we know this better be the answer. But what happens if we just sort of naively add using the algorithm we just saw? So the 1/3 gets replaced with these functions f of 1/3. I'm doing an uncertainty of 2, so my n is equal to 2 here. And so I get this expression, f of 1/3 of 2 over 4, and then add that same thing twice. What we had just seen was that these were each 1/4, right? 1 over 2 squared. That adds up to 1/2, 2 over 2 squared. But 1/2 and 3/4 are not the same thing. So there's some uncertainty that we're screwing up here. And the problem is with our addition formula. So here's how we replace it with a more superior one that doesn't get those errors. Okay, it looks a little bit messy, but it's not so bad. Here's the argument. Suppose I have an x and a y. Now I want to figure out what number is x plus y. And remember, I'm representing the number x plus y with this function f sub x plus y. That's what I'm trying to figure out. We have set a particular precision of n. We're going to add fx and fy, but with more precision than we need for the output. We're going to do it 2 bits more precise. Like if I want my final answer to be within 1 over 2 to the n, I'm doing these intermediate calculations for 1 over 2 to the n plus 2. Having the 2 to the n plus 2 has 4 more in the denominator, so I have to scale it a bit, correct for that scaling. And then what I finally get is something I can round to the nearest integer. And the argument is that now when I do this, it is accurate within the uncertainty of 1 over 2 to the n. So let's see how it works out in our specific example. Remember, we were doing 1/3 plus 1/3, so let's do that there. F of 1/3 plus 1/3. Remember, we already know the answer. Like, we know what f of 2/3 should be. You and I know the 1/3 plus 1/3 is 2/3. The answer better be 3, because 2/3 round to 3/4, and the numerator of 3/4 is 3. So we know the answer better be 3. Okay, so in my formula, it tells me I have to do f 1/3 of 4, but that's 5. We've seen that in our chart before. Here we're rounding to the closest 16ths, and 5/16 is the closest one to 1/3. You can check that inequality. Okay, well, let's plug that in. So if this f 1/3 evaluated at 4 is equal to 5, so my numerator is going to have 5 plus 5 over 4. That's 2.5. 2.5 rounds up to 3, and look at this, now our 3s are actually going to match. So this time we don't have the error. And I'll leave it as an exercise for you to check in the comments that with this formula, you will always have an error less than 1 over 2 to the n, and so that works out great. This is the sufficient formula to guarantee the right degree of accuracy. So really what recursive real arithmetic is doing is now 2 things. It's replacing a number with this function. And this function allows you to get to arbitrary levels of precision. You give me a higher level of uncertainty, 1 over 2 to a larger n, and I can give you the corresponding numerator of the dyadic rational. The arithmetic all works out great. I can add things that are represented in this way. And there's similar algorithms for multiplication, for inverses, for roots. They get a little bit more complicated. Like for multiplication, you have to have the multiplication of the errors and the magnitudes of the numbers themselves. But you can check all the formulas out if you're interested in the references and the paper that I'll put in the description. And then also note that you can go beyond just these basic things to like exponential and sine of x and cos of x. All of these transcendental functions have Taylor series expansions. I'll put a link to my Taylor series intro for those who aren't aware, but if you've seen calculus, you know that a lot of these functions can be represented as these sums of x to the n's with coefficients. Well, if I just do an approximation with a Taylor approximation, that's just more sums and more additions. I already know how to manipulate the level of uncertainty. Like in our addition formula, we went 2 steps further to the right in our uncertainty. Well, this will tell you how to get as far as you need. And I'm burying stuff under the rug. There's tricks here, like these are the Taylor series about x equal to 0. If you're very far from x equal to 0, they converge very slowly. So there's tricks like scaling, where you take a number, you scale it something close to 0, you perform the Taylor series there, you slide it back up. There's other tricks I'm burying, but the basic idea is that numbers are replaced with these functions with variable uncertainty, and you can play around with the uncertainty to be as arbitrarily precise as you wish. So while before rational numbers were great because you do these exact approximation, Recursive reals have now generalized to all the irrational numbers, and you get the sort of arbitrary level of precision. That's also really good. But they have a problem, and the problem has to do with decidability. So contrast these two expressions, cosine of pi minus cosine of pi and e to the minus 100. Now, they're both kind of zero, but the kinda is doing the heavy lifting. Like the first one is exactly zero, and it should output on your screen 0. It would be kind of bad if it outputted 0.000000. That would indicate just an approximation based on the number of digits that you had on your calculator screen. I want it to realize that this is truly identical to infinite levels of precision to 0. E to the minus 1000, though, it isn't exactly 0. It's the tiniest bit away from 0. A couple choices here. One thing you could do is you could output this as 0.000000 just to indicate that it's very close to 0 within the uncertainty of the number of digits that you're displaying on the screen. That would be more helpful than outputting identically 0, which would imply a different thing. It's sort of a user experience thing. Like, what do humans expect? How do they interpret the difference between 0 and an approximation 0.0000 to some number of digits? Now, both calculators don't actually do quite this. The Android calculator gives an even better answer. It calculates it as something to the order of 10 to the negative 435. And this really leveraged the recursive reals. Because the recursive reals could get arbitrarily precise, they weren't limited the way floating point numbers were. They could go all the way to the correct final answer. For iOS, they're using floating point arithmetic, and there is a lower bound to how small of a number you can represent. I think it was 10 to the negative 308. But this turns out to be like 10 to the negative 435. It's below that minimum cutoff for floating point numbers. So the iOS calculator displays underflow, and what that just means is they were trying to compute it and it dropped off that minimum threshold. They don't know how far it dropped off the minimum threshold. They're just going to report out underflow so we know that it's less than the minimum. That's all they're going to tell us. So these are user experience choices, whether you choose 0, whether you choose 0.0000, whether you go all the way to its exponential form, whether you write underflow. These are all user design choices about deciding whether things are or are not actually equal to 0 and how you would like to display that to human users. The problem for recursive reals, though, is how do they know that cosine of pi minus cosine of pi is equal to 0? I know you and I see that they're the same thing, you just cancel. So for the recursive reals, let's say you take it to the same degree of precision and you see that they're the same. So you go a little bit further, you get a bit more precise, a higher value of n, they're the same. A higher n again, they're the same. A higher n, when do you stop? So for the recursive reals, for their incredible power to actually come along here and compute out these correct answers, they have a decidability challenge. So here's how this is implemented to try to get around this. A number is now leveraging the best of both worlds. It has a rational part, which is great. We can do exact representations here and we can compute stuff out really nicely. And then also a recursive real part that has this ability to scale the level of precision. It's the product of two of these things, something like 2 times pi. And then there's a third thing which is called property. Property is a flag or a label. And it's something like being pi, or being the square root of an argument, or e to the argument, or logarithm of an argument. It's waving your hand and saying, by the way, this number that I'm doing, it came about from the number pi. Like, so for example, say I have 2 pi and I want to approximate that to 4 decimal places. The way you'd store that is a rational number 2, then a recursive real to 4 decimal places, 3.1415. And then finally, the property would be that it came from pi, so you flag it with the symbol pi. This is not like the infinite number of digits of pi, it's just like saying it's the first thing on my list of potential flags. Like you might even put the number 1 there if your properties were enumerated the way I've listed them. It's just to say, by the way, the 3.1415, it wasn't like pi plus e to the negative 1000, which would also approximate to this. It actually came from pi. It's a way to keep track of its origin and allow you to reproduce the recursive real part. Okay, so why is that nice? So imagine I have something like, 2 pi minus 2 pi. That's the user input. To us humans, they should cancel and it should be identically equal to 0. iOS has no issues with this. They're just doing floating point arithmetic. You plug those in for floating point arithmetic, you get the exact same string, so they think of them as being exactly the same. They'll output 0, no problem. The recursive real part's the tricky part, but now we have a solution with that property flag. I'll take both of these and represent them. It's a rational number, either 2 or minus 2, times the 3.1415, and then they have the same property flagging that these both came about from pi. So now the algorithm looks at this and it says, same recursive real, same property, all I'm going to do is deal with the rational part. 2 plus minus 2 is 0. It keeps the same recursive real part. It keeps the same property. But then what it does, it displays on the screen, this is 0 times that, it displays out identically 0. This blocks having this blow up where you're just going more and more and more precise, always finding them the same, but not sure if they're identically 0. Because they have the same property flag, we can use just the rational arithmetic and get that they're equal to 0. In contrast, if the user inputs something like pi plus root 2, these have different property flags. So the one is going to be written as 1 times 3.1415 with the pi property flag. The other is 1 times 1.4142 with the square root property flag. Those are different things. And so what's going to happen, it just says, well, now I have to do not rational arithmetic, I'll use the recursive real arithmetic. It does that and gets, say, 4.5558, and to the user will output just that 4.5558. It also changes the property flag. Pi and square root, they don't combine to be like a known enumerated thing, property that we've identified. So it gives a more general property, just as it says an irrational number. The irrational number part lets us, the calculator, know that if it needs to use this, it's going to use the recursive real part of it, not the rational part, which is just 1. So basically, the implementation on Android here is leveraging the strengths of the rational and the recursive real parts, and it's putting them together such that it's never going to lie to you the way I'll call the 10 to the 100 plus 1 minus 10 to the 100 thing. I'll call that a lie on iOS, although what I more correctly mean is an approximation in floating point arithmetic. It's not going to make those kind of errors, and it's going to decide between 0 and 0.00000 as often as it can. But it's not perfect. I'll show you one example where the iOS answer superficially almost appears better. If you type pi squared minus pi squared equal to 0 into iOS, then it's going to give you it equal to 0. But what iOS really means is not that it knows that these are identically 0, it just means that the floating point approximations for pi squared is the same as for pi squared. And so when you subtract them, you get the 0 floating point number, and it always displays that as 0. So even though it's got that identical 0 symbol there, it still should be thought of as an approximation at some level. It doesn't know that it's identically 0. In contrast, why is Android giving 0.0000 the symbol that it preserves for when it's approximately 0, not identically 0? And the reason is that those property flags is a limited list. It knows pi is a special property, it pulls it out. It knows square roots are a special property, it can identify those. But it doesn't have powers of pi listed. And you might then be like, well, Trevor, couldn't they have put pi squared in as a special property so it would know this? Well, yeah, but then you'd have every possible power of pi. How do you deal with that? How do you deal with all the combinations that you might be interested in? That would lead you down the road to something called an actual computer algebra system that can deal symbolically. The Android calculator isn't trying to do that. It's just a couple thousand lines of code for its core API implementation, and it's meant to be fast and efficient and deployable on a calculator without taking up a lot of space. That's its goal. If it wanted to be a Maple or a Mathematic or one of these sort of larger computer algebra systems, well, they could do that. So the real strength of this method is not like the right way to calculate things forever and into the future. It's sort of a thing very tailored and optimized for specifically calculator apps and trying to make the user experience better. Now, if you think I'm just here to hate on iOS, I mean, I have an iPhone myself here, and there is an argument to do it with just the floating point numbers. Yes, the floating point number approach will mean that things are approximated, that you'll get errors like that 10 to the 100 error, that you'll get things like the underflow. But floating point numbers are entirely predictable as to what the errors are. You know exactly what it's doing, you can figure out exactly what it's doing, and there's never any worry about like, how exactly is this being implemented to get this? If you know your floating point arithmetic really well, you should be able to predict exactly its behavior. There's a strength in that as well, even if it leads to a user experience that contradicts how humans typically think about math when we do things like 10 to the 100 plus 1 minus 10 to the 100. So even though the implementation isn't really respecting those types of problems, there's still a lot of strength to floating point arithmetic. Now, if you want to learn about how more than just calculators are going to work, I strongly recommend the sponsor of today's video, which is Brilliant.org. Brilliant has thousands of lessons across math, science, computer science, and their lessons are designed to really build your foundational understanding so that when you're playing around with neural networks, say, you understand all the mathematical ideas underlying them and really can understand what's going on. Their lessons are really interactive, putting you in the driver's seat, playing around with the animations, and constantly testing your understanding. When I used Brilliant to help me learn Python recently, I found that doing a little bit every day for a couple weeks was phenomenal for developing my mastery of Python because Brilliant didn't let me be lazy. I was always involved in the coding process, and that's what helped ensure that I really had understood the content. To try everything that Brilliant has for free for a full 30 days, go to brilliant.org/TrevorBassett. That's me, or click the link down in the description. And clicking that link will also give you 20% off an annual premium subscription. With that said and done, I hope you enjoyed the video. If you have any questions or your calculator is doing something really weird, tell me about that down in the comments, and we'll do some more math in the next video.